Hello everyone. Here we present Cohort, software-oriented acceleration for heterogeneous SoCs. Traditionally, we must optimize accelerators to the maximum, leaving software to fix any hardware-software mismatches in programming interface. This requires a deep knowledge into hardware to program the accelerators efficiently in software, which we consider to be hardware-oriented. In this paper, we present Cohort Engine, which provides the accelerators and software a unified software queue semantic to interface with one another. Here we show the software code needed for invoking a single accelerator with Cohort. Our approach demonstrates as much as 10x speedup over traditional DMA while retaining software semantic. Here, we show the software code needed for invoking two accelerators with Cohort to do encryption and hash. Conceptually, they are no different from invoking two different software threads for computation. Please come by and attend our talk at the first session in ASPLOS this year. Our session is located in session 1B, Monday, March 17th, 10:20 a.m.
Hello, I'm Chase Norman, and this is PipeSynth. Formal verification requires formal models of the system being verified. These are tedious and error-prone to write by hand and difficult to write for non-experts. This is particularly the case for microarchitectural ordering models used in memory consistency verification. Prior techniques for the synthesis of microarchitectural specifications required RTL as input. We introduced PipeSynth, a tool for the automatic pre-RTL synthesis of microarchitectural ordering models in the domain-specific MuSpec language, using program synthesis techniques from formal methods. Pre-RTL synthesis allows the synthesized specification to be used for early-stage verification, which can catch bugs earlier and reduce overall hardware development time. As inputs to PipeSynth, the user provides a partial MuSpec specification, as well as litmus tests and execution traces describing forbidden and allowed outcomes. PipeSynth then automatically synthesizes additional MuSpec axioms to complete the MuSpec model, such that it allows and forbids the outcomes specified by the execution traces and litmus tests. To make MuSpec synthesis feasible, we develop a novel synthesis encoding, which eliminates many redundant and nonsensical possibilities from being considered by a synthesis solver. Our technique can synthesize an entire specification for the multi-V-scale processor in under 1 hour. We can also concurrently synthesize 4 or more axioms on other microarchitectures, including an out-of-order processor and one with a non-traditional coherence protocol. We hope to see you at our talk in session 1B on Monday morning.
Hi, I'm Burcu, and I'm going to introduce our recent work on probabilistic concurrency testing for weak memory programs. Weak memory programs are hard to get right. They allow for a wider set of program behaviors than what's possible under the interleaving semantics. Take the example here. Under weak memory, it's possible to have an execution that sets 0 to both A and B, which is not possible in any interleavings of the threads. The question we explore in this work is how to test weak memory programs efficiently to check if the program can exhibit some unwanted behaviors. A promising idea is to apply probabilistic concurrency testing, PCT, which comes with good guarantees on the probability of finding bugs. The guarantees of PCT relies on its characterization of concurrency bug depth, defined based on the scheduling ordering constraints to produce the bug, which does not apply to weak memory behaviors. In this work, we present PCT weak memory, which generalizes PCT to weak memory concurrency. We achieve this by generalizing the definition of concurrency bug depth. It is not tied to event orderings anymore, and accordingly generalizing the algorithm and its probabilistic guarantees. PCT weak memory is a memory model agnostic algorithm, and its theoretical guarantees apply to any memory model.
Hello, my name is Reese Levine, and I will be presenting MC Mutants, Evaluating and Improving Testing for Memory Consistency Specifications, which is joint work between UC Santa Cruz and Google. A memory consistency specification defines the allowed behaviors of shared memory parallel programs. A parallel programming framework, which consists of a language, compiler, and architecture stack, implements an MCS. MCSs are complex, Previous work has developed testing techniques and found bugs in MCS implementations. However, these tests are non-deterministic, so they must be run for many iterations and with added stress. So the question remains, how do we know the tests caught the bugs they were searching for? Previous techniques explored a limited state space of test outcomes, missing bugs. We develop a novel mutation testing strategy which relates bugs in tests to allowed weak behaviors in mutants. We then can develop novel testing techniques which uncover more mutants and by extension help us find new bugs or give us confidence that bugs don't exist in certain areas. We evaluate our methodology using WebGPU, a new GPU framework that runs in the browser. We find 2 new MCS bugs, one that led to a change in the WebGPU specification. Our MCS tests have also been integrated into the official WebGPU conformance test suite, which must be run by many browsers as part of their development process.
Hello, my name is Martin Beck. I'm from Huawei Dresden Research Center. This is the lightning talk for Atomic. A major part of large software was designed for x86. It has run stable for years. Recently, many companies are migrating their software to ARM-based servers. Bugs appeared due to the weaker memory model of ARM CPUs. There are numerous examples of such bugs, and it takes a lot of time and effort to fix them. How to do that efficiently for a large codebase is an open question. We propose a new static analysis approach to detect memory locations causing such bugs. The analysis can be divided into 3 steps, which are the analysis of code annotations, memory aliasing, and code patterns. An important pattern that we try to detect are spin loops used for thread synchronization. In the end, all relevant memory accesses are made atomic. We have applied atomic to production software like MariaDB and Postgres. On the figure, the dark red bars refer to the normalized performance of the application. Yellow depicts the performance of the atomic ported binaries. Blue represents a naive transformation with all memory accesses turned into atomic. Atomic has an average performance impact of 1%. By this we show that our automatic approach scales to millions lines of code with minimal performance impact and minimal human intervention. Thank you.
Hi everyone, let me introduce Risotto, our dynamic binary translator for weak memory model architectures. In the last few years, we are seeing an evolution in the CPU market, with the ARM architecture being used outside the embedded world, with major vendors such as Apple, Microsoft, or Amazon building desktop or server machines based on ARM CPUs. Most major cloud providers also offer ARM-based instances that are more cost-effective than their x86 counterparts. But what does this mean for software developers that want to use these? Let's say you have an x86 application that runs in the cloud. If you have the source code and there is no handwritten x86 specific code, then you can probably just compile it for the ARM target and run your application without any issue. However, in practice, that's not always the case. So if you don't have the source code, you need to run your x86 binaries directly on ARM. To this end, we introduced Risotto, a dynamic binary translator for weak memory model architectures with a focus on performance and correctness of the memory model. Risotto is a dynamic binary translator that emulates x86 binaries on ARM v8 processors based on the widely used QEMU emulator. Risotto introduces new memory mapping schemes that precisely replicate the strong x86 memory model on the weakly ordered ARM architecture. In addition to the implementation of these mappings, we formally prove their correctness. We also provide a dynamic host shared library linker that allows Risotto to use the native ARM version of shared libraries instead of translating from x86, as well as a native and correct translation of compare and swap instructions. You can check out our paper here, and we'll be happy to see you for our talk on Monday, as well as have a chat with you during the conference.